Hello everyone, and welcome to a little bit of a different kind of video today. So in this quick breakdown, we're going to explore how a software PWM signal is generated to control a servo motor. So we're just going to be using C code, and there's going to be no special PWM module. We're not going to use MCC to control this PWM signal or even generate it whatsoever. Let's first go over what PWM means. PWM is Pulse Width Modulation. That's the acronym. And PWM is used to control devices such as servo motors by turning a signal on and off for precise duration. So a typical servo revolves at 50 hertz. So we got a pulse every 20 milliseconds. That's the period there. And the length of the pulse will determine the servo angle. That pulse usually is a duration of 500 to 2500 microseconds. And if we have a special attachment for the servo, we can actually mimic 360 degrees. So that's pretty cool. But this method is not just for servo motors. We're just kind of using that as a baseline because it's pretty simple. This method works for all PIC microcontrollers. Pretty cool because who wants to spend all that time going through MCC when we can just generate it in software in a few lines of code. How is it done in software? Well, we will set a pin high, and then we will wait, and then we will set it low, and then we will wait again, and then we'll set it high again. So that cycle there is a PWM signal, because to a device that acts off of PWM, all it needs is on and off in a set duration of time. We're going to open MPLAB X. So I have something already here finished. This code is precise, it works great, but what we're going to do is we're just going to enter our source files here and create a new text file. We're going to just call this PWM tutorial, and Mood Tracker is just a project that I've been working on, and you guys should see a video on that pretty soon. We will go back to our main file. Let's see what I've written here. And as you can see, you got a whole lot of mumbo jumbo, but honestly, this is some pretty simple code here. It is just a alternating LED that is synonymous with angles of the servo. This is the function that will help us control the servo, ensure that its period is 20 milliseconds, acting at a frequency of 50 hertz. When we press the button and we want to switch states of LED and also angles of our servo, we want to ensure that the 20 millisecond period holds true still. And we need that to happen with accuracy. There needs to be precision when the signal is being sent to the servo. We're going to talk about how to write this function. We're going to break it down, make it very simple. We're going to pass in the argument of an unsigned integer that is the microseconds for how long that pulse is going to last. So unsigned integer means that this is an integer. Unsigned meaning that it cannot be negative. This is only a positive integer because when we're talking about time, it must be positive. So we're going to use an unsigned integer. And this is the name of our function, delay_remaining, because what we're going to be doing is we're going to be iterating through our period in chunks to maintain accuracy. So the purpose of this function is to delay for the remaining time in a 20 millisecond period after the high signal has been sent. So we are sending a high signal and we want 20 milliseconds to transpire with the duration of this signal. This ensures that the 20 millisecond cycle is maintained. That is because it is a 20 millisecond period for servos. So now we're going to write our function. What we want to do is we want to calculate the amount of time that is remaining after our high signal. To calculate it, we'll need to create a variable, and that variable will be an unsigned integer. We can call this remaining. So the remaining time will be calculated in microseconds because MPLAB X IDE, you cannot have a decimal. So our first variable of the function is the remaining in microseconds. This will be equal to our 20 milliseconds, which is 20,000 microseconds, minus the high signal. So this value here is actually our argument, and it will be passed in when we put in our value here, and this variable will help us calculate the remaining time after the high pulse. To maintain accuracy, we're going to delay in chunks. We want it to be 1000 microseconds per iteration, while the remaining time in microseconds is greater than or equal to 1000 microseconds. We shall delay by 1 millisecond. Is we're going to make the value of our remaining equal to itself minus 1000, and that is 1000 microseconds. So we can continue on. And what we're doing is we're just delaying in chunks. When we have over 1,000 microseconds left, we're fine to just delay by 1 millisecond. So for ease, we're going to make this value 500 microseconds. This is our total period in microseconds, and this is just our high pulse. Let's say this is 0 degrees. This value now is equal to 19,500 microseconds. 19,500 microseconds needs to be delayed to ensure that we get our 20 millisecond period still. For 19,000 microseconds, we're going to just delay as a single function of 1 millisecond. And once we get to the 500 microsecond, we don't want to delay by a millisecond because that's not going to give us our 20,000 microseconds. We're going to have delayed for 20,500 microseconds, which is not 20 milliseconds. So now what we're going to do is, while the remaining microseconds to achieve 20 milliseconds delay is greater than or equal to 100, delay by 100 microseconds. This means that for the 500 microseconds that was left here, we're going to just delay it by 100 microseconds. And that will allow us to achieve the perfect 20 millisecond delay. For something like a 500 microsecond signal, that's all we need. And we need to make sure that we are setting the value of the remaining microseconds as itself minus 100 microseconds. Delay in 1 millisecond chunks for remaining time greater than or equal to 1 millisecond. We are going to delay in 100 microsecond chunks for a remaining time greater than or equal to 100 microseconds. What happens if this value is like how I have it in my code, 475? Well, now this value is not as pretty. It's not as simple. This value has actually become this. This is what's left. This is how much we have to delay. And now this isn't going to fly. We're going to need something to get rid of this 25 because we're going to delay 19,000 microseconds in 1 millisecond increments. And then we're going to delay 500 microseconds in 100 microsecond instances. How are we going to delay that? We can't delay that with 100 microseconds. We want to make sure that our function always works. So we want to delay in 10 microsecond chunks here. And then now for our last function, it will be a 1 microsecond chunk. And what you might notice is we have just written the entire function that we had on the first page that I showed you. That was writing a systematic function that will allow you to create a PWM signal in software. And I can go to this program here and show you my MCC file. This is a pretty standard default setting, and it works. It's pretty simple. Just wrote a function logically, and you're able to achieve PWM signal without having to go through, this guy over here and figure out your timer, and then go through your CCP, and then, oh no, only got 2 pins that I can actually use CCP, so I might need to go to the enhanced version and then go about it this way. We don't need to go through this kind of crazy stuff here and figure out all your registers. You don't need to do that. It's very simple. You just write a program. It's great to be able to configure your hardware, but on a time crunch, and also like as a test for yourself and your coding, create a function. It's great and it's simple. All right, well, that was all I wanted to show you guys for today, and I hope you enjoyed.